before the snowstorm on Wednesday.
We had the following situation. We're told that a bunch of data, which really means that we have like a histogram of a lot of data,
Follows a bell-shaped curve. You can make the histogram, you're going to get a bell-shaped curve.
the middle value of that whole population, we'll call it population X equals female weight. The average female weight is 120 pounds.
Of course, I have no idea if this is true, I'm making these numbers.
The standard deviation of
Well, what number did they put down on the board so it'll be consistent? What was it? 20.
20 pounds. Sigma equals 20.
It was 15 for the males.
10 for the females.
Of course, it could be any number. It's got to be a positive number, but it's got to be, right? Now, the question was,
For example, how many females weigh more than 120 pounds? How many females weigh more than or equal to 120 pounds? Let's start out with that one.
well, again, I'm not going to repeat the whole theory of chapter 6 right now, but we figured out last time, since it's based on a histogram, the area under the curve corresponds to the probability, or equal to the probability. And the area goes from here to here is 100%. It's mirror images are symmetric on the left and right side, so each side is 50%. And how many people weigh more than 120? Well, those are the people, the area under the curve that corresponds to 120. I'm shading in right now. And that's literally half the diagram, so the answer is 50%. 0.5, half, whatever else you want to reduce it to. How many people weigh 100, more than 120 or equal to 120? Well, this chapter, since we're dealing with continuous random variables, nobody weighs exactly 120.0000000 and 10,000 zeros, and therefore this is going to be exactly the same thing. Then we asked ourselves, how many people weigh between 120 and 130? Well, where's 120? 120 is there. Where's 130? Well, if you go 10 in this direction, you go straight down. 10, I mean, this is 10 points right over here, so 120 plus 10 is 130. So 130 is over here. So essentially, it's the area that I'm shading in over this chunk over here. And if you look at it, we decided last time we just literally looked at it. My picture's not that perfect, but it's roughly approximately correct. It looks like 35% of the area, and I told you to memorize when we learned today where that comes from, that it's 34% of the area. So the answer to the question is 34%, which means automatically how many weigh more than 130? Well, that's got to be 50, take away 34%, because this whole piece is 50%. If this is 34, that's got to be the missing 16%. So by a simple subtraction. And finally, since I'm doing all the homework for you, which is really not my usual policy, it's just important to get this straight. Usually if nobody did the homework, I would just simply skip over and move on to something else. How many weigh between 110 and 130? Well, if you go 110, you go 10 in the other direction. There's no reason why you can't go 10 in the other direction. So 110 is over here. There's 10 points in here. So now we're talking about this whole piece. Well, this is 34%. This also got to be by symmetry 34%. So the final answer is, and since areas are additive, the answer got to be 68%. So if you follow that, you understand everything I told the class on Friday or Wednesday. And if you have any questions about any of the numbers or the pictures on the board, now's a good time to ask. Before we go into more advanced stuff, it's good to get the basics straight. Any questions about any of the numbers or pictures, or there's no formulas yet, it's just numbers on the board. Well, the question that we're going to focus on today is, what's the probability somebody weighs between 120, which is the average weight, and instead of 130 that we had before, now we're going to move it to 131. So to make the picture a little bit clearer, let's start again. We have a bell-shaped curve. We're always told that at the beginning of the problem. We're told that the middle value is, we call the original one X, and it's female weight. And the middle value, which is symbolized by the mu, is 120. The sigma is 10. And 100, this is 10, and this is 120. 121 is simply a tenth, but this is 1/10 of that. So 121 is just basically around here. So we want everybody between this spot and this spot. And I think we said in class last time, I'm pretty sure somebody told me that, well, if this from here to here is 34%, 120 would be 34%, this little piece here can't be that much, maybe 1 or 2 or 3 percentage points, so the answer got to be, instead of 34%, maybe it's 35 or 36. So let's put down approximately 36%. That's what the answer, based on common sense and looking at the picture, should give you. The only question is, what is the exact answer, not based on guessing, but based on a formula, or based on some kind of a table or diagram or calculation. And the answer is, there's a table that will give us the answer, and that table is called the Z-table. The Z-table is found in the back of the book, or the front cover of the book. This is so important, this is a little sloppy. Let me try to make it a little bit better. And essentially what we have to do is convert this picture to the what's called the standard normal distribution, called the Z diagram. This is really messed up. I should do a better job of that. It's called the Z. And that's the name of the Z is a standard normal distribution. And the reason why it's standard is because it's set up in such a way that the middle value is 0 and the sigma is 1. In other words, somebody took a bunch of data that has a middle value of 0 and a sigma of 1 and tabulated the different areas under the curve for this particular specific 0 and 1. But our problem has a mu of 120 and 10, not 0 and 1. So the trick is, how do you go from one to the other? And it's comparable to going from feet to inches or pounds to kilograms and miles to kilometers. You just got to convert it. And the formula is very simple. This is the only formula from chapter 6 that you need. And basically it says the following. You take the original number, convert it to a z-score. We learned how to do conversions. I think the formula you're familiar with from chapter 3 is x minus x bar over s. How many people are familiar with the z formula from chapter 3? We all are. Except now we're not dealing with a average of a sample, we're dealing with the average of the population. We're not dealing with the sigma, or the standard deviation of a sample, we're dealing with the standard deviation. It's the same idea. And another way of looking at this formula is by subtracting. Let's try to apply the formula to our situation. We want to know if somebody has a weight of 121, which is the question. Where's the question? Oh. If somebody has a weight of 131, this is the question we're focusing on right now. If somebody has a weight of 131, what is their z-score? Well, somebody who's 131 is about 11 points above the average, but 10 pounds represents 1 standard deviation. So the question is, how many standard deviations above the average are we talking about? Well, 11 pounds is about 1.1 standard deviation. So to do that, we do 1 minus the average. The sigma, again, we told these numbers at the beginning of the problem. That's equal to 11 over 10, and that comes out to 1.1. And you'll see we really should take it out to a second decimal place, 1.10. So another way of thinking about this formula is by subtracting 120 from everybody, we shifted everybody over by 120 pounds, so the new average is going to become 0. And likewise, by dividing everybody by 10, the new standard deviation is going to be 10 divided by 10, or 1. So there's a certain simple common sense reason why this formula works. But the easiest way is to relate it to the formula from chapter 3. Anyway, either way you look at it, we now know the area that we really care about is somewhere between 120 and 121. Where does 121 correspond? I'm sorry, 131. This should be 131. 131 is the problem we're trying to solve. So it corresponds to a z-score. 131 corresponds to something similar part of the diagram, namely a little bit to the right of 1 standard deviation. In fact, it comes out at 1.1. This is 1 over here. 1.1 is roughly right over here. So again, to repeat. Now, by the way, what does 120 correspond to? Well, you should just memorize that the middle value always corresponds to a z-score of 0, because 120 minus 120, of course, is going to be 0. So you don't have to actually calculate it or make a picture. But basically, after all is said and done, I'm not sure if I was totally clear the last couple of seconds, we want the area between a z-score of 0 to a z-score of 1.1. So let me repeat. The original problem says, how many people weigh between 120 and 131? That's equivalent to figuring out how many people weigh between a z-score of 0 to a z-score of 1.1. That's what we're up to at this point.